beam, you have to know what is T-beam. Look, T-beams are just same as simple rectangular beams, which are casted monolithic with slab, which means the slab and beam is casted at the same time. Now, due to which the portion of the slab act as the part of beam. This diagram is explaining my words, and with a central line T-beam is located here. So in this diagram you can see the slab and beam is casted monolithically, right? It is considered that the beam at location other than supports act as T-beam, which means at the midspan and nearby midspan, the flange portion, which is part of slab, act as a resisting part along with rectangular beam for the applied bending moment. But this flange portion is effective in resisting the bending moment only cause for shear force, only wave is effective. Okay. Look, this is the T-beam. The two terminology I have just used, one is flange and another one is wave. Now, which portion of this T-beam is flange? That upper portion shown in figure, the head portion of the T is called flange, which is a part of that slab which is casted along with this beam, and this lower portion is called wave. Okay. B suffix f, small b suffix f is width of flange, as you see in figure. Capital D suffix f is depth of flange. Small d suffix w is depth of wave, and small b suffix w is width of wave, and overall depth is capital D, and effective depth from the top of the flange up to the center of reinforcement, which is effective depth, is small d. Now I will discuss the terms briefly which used in T-beams. First is breadth of wave, that is BW. Breadth of wave is the width of the beam supporting the slab. It would be sufficient enough to accommodate the tensile reinforcement properly. The main reinforcement, actually the ratio of the width of wave to the depth of wave is kept as 1/3 to 2/3. Now thickness of flange, that is D suffix f. The thickness of flange of T-beam is equal to the thickness or depth of wave forming the flange of beam. This is the flange of beam, as you've seen earlier. Okay. Now overall depth, that is capital D. Overall depth of a flanged beam is equal to the sum of the depth of flange df and depth of the wave dw. It is generally assumed as 1/12 to 1/15 of the span in case of simply supported beams, but for continuous beams the overall depth is assumed as follows: for light loads 1/15 to 1/20 of span, for medium loads 1/12 to 1/15 of span, and for heavy loads 1/10 to 1/12 of span. Okay. Now effective width of the flange, that is BF. It is that portion of slab which acts integrally with the beam and extends on either side of the beam, forming the compression zone. The effective width of flange mainly depends upon the span of beam, thickness of slab and the breadth of the web. Okay, so these three things is the depending factor for effective width. It also depends upon the type of loads and support conditions. Now the effective width of flange should not be greater than the breadth of the web plus half the sum of clear distances to the adjacent beam on either side, as shown in figure. Okay. Now the effective width of compression flange of the flange beam can be calculated as follows. Okay, T beam is also called flange beam because it has a flange portion. That head of T is called flange, so this is also called a flange beam. So this consideration are from clause number 23.1.2 of IS 456 2000. For T beam, BF is equals to L0 by 6 plus BW plus 6 DF, and for L beams, this at left side, this is L beam. Okay, and for L beams, BF is equals to L0 by 12 plus BW plus 3 DF. Okay. For isolated beams, the effective flange width shall be obtained as below, but in no case greater than the actual width. You have to remember it. Okay. Now, so for isolated beams, isolated T beam, BF is equals to L0 by L0 by B plus 4 plus BW, and for L beam, BF is equals to 0.5 L0 by L0 by B plus 4 plus BW. Okay, this calculations is for isolated T beam and L beam. Okay, now the terminologies, all terminologies you have know except L0. So again I like to discuss the terminologies. BF is effective width of flange, you know. BW is breadth of or width of web. Capital GF is thickness of flange. Small b is actual width of flange. Now L0 is distance between the point of zero moments. Now for continuous beams, L0 is taken as 0.7 times of effective span. Otherwise, which length is given for flange in question, we can use that length as L0. But for continuous beam, we have to take 0.7 times of effective span. Okay. Now we will analyze the T beam. Look, T beam is considered is just like rectangular section, as you can see in earlier videos, which links is given in description box. So there is mainly two cases may arise. First one is neutral axis may lie in flange portion, and second case, the neutral axis may lie in web portion. In these two cases, the method of analysis is slightly different. The section division is slight difference. Okay. So first we will consider first case when neutral axis lies in flange portion, but the basic considerations are same for both cases. Now consider a T beam having flange width of BF, web width of BW, and flange thickness DF as shown in figure. The beam is reinforced with area of steel AST in tension zone. Okay. Look, as you see in figure. So leftmost portion is section. Figure B is strain diagram, and figure C is stress diagram or stress block. Okay. Now, in this case, analysis of T beam, in first case, XU is less than DF. That means neutral axis lies in flange section. Okay. So for strain diagram, then uppermost fiber is, as you can see in figure, is 0.0035 and that lower portion is 0.002, and in tension zone 0.87 Fy by ES plus 0.002. Okay. This method of analysis is just like rectangular section, rectangular beam, as you learned in previous video of single reinforced beam by Limestad method. Okay. So these terms, this maximum limit of values are known to you, which have seen the who have seen previous videos. Okay. For stress diagram, for upper outermost fiber, the maximum limit is 0.446 FCK or 0.45 FCK, and there is two division, 3/7 of XU, that is 0.42 XU, and the rest portion is 4/7 of XU. We will discuss about this all terms. And in tension zone, T is 0.887 FIST for stress diagram. Now look, now I will explain this all terms which have you see in figure. The stress block shown is similar to one of the rectangular section, as I said earlier. So maximum compressive stress 0.45 FCK or 0.446 FCK. Okay. Rectangular portion DCBE and parabolic portion EBA. Look, rectangular portion is DEBC or DCBE, and parabolic portion is BEA or EAB. Okay. Now EB corresponds to strain 0.002 in concrete, right? And DE is 3/7 of XU and EA is 4/7 of XU. Now depth of neutral axis and moment of resistance. Now there are two cases. First, neutral axis falls in the flange, as you've seen in figure. This is the first case, as I told you earlier, XU less than DF. And second case is neutral axis falls in the wave, that is XU greater than DF. So that figure I have also shown you. Okay. So case 1, XU less than DF, that means when neutral axis lies in flange portion. Now depth of neutral axis, if XU less than DF, the section will behave as a rectangular section having width of BF, width is equals to BF. Depth of neutral axis can be found from the equation used for rectangular section after replacing B for BF. So the depth of neutral axis XU is equals to 0.87 FYST by 0.36 FCK BF. This formula is known to you, which I have written in Annex G of IS 456-2000. We have just replaced B for BF. Now moment of resistance, mu. Comparing XU and XU max, the determining the type of section as follows: XU less than XU max, the section is under reinforced and moment of resistance of section is given by mu is equals to 0.87 FYAST within bracket D minus 0.42 XU. This formula is also known to you. You have learned earlier in rectangular sections video, single reinforced beam video. This formula is taken from Annex G of IS 456-2000. Now, if XU equals to XU max, that means the limiting value, the section is balanced and moment of resistance can be calculated as mu lim is equals to 0.36